Alkanes are fascinating in their simplicity, being saturated hydrocarbons with single carbon-carbon bonds. Dr. Ayabami, could you explain how these strong covalent bonds affect their reactivity?
Absolutely. Alkanes exhibit a tetrahedral structure with 109 5 bond angles. This saturation stabilizes the molecules, making them generally unreactive. However, they still react through processes like combustion and substitution where UV light is essential. For instance, methane reacts with chlorine.
Interesting. But given their stability, could the inert nature of alkanes pose challenges for practical applications?
Certainly, their stability means we can't easily alter them without significant energy input. This is why, although useful for fuels due to their combustibility, alkanes aren't as versatile in chemical synthesis compared to unsaturated compounds like alkenes.
Moving forward, how do researchers see the role of alkanes, particularly in our transition to sustainable chemistry?
The trend is towards more efficient catalytic processes that harness alkanes' energy potential while reducing emissions. Futuristic applications might involve cleaner combustion methods or converting alkanes directly into value-added chemicals in a more sustainable manner.
Alkenes are known for their chemical reactivity, thanks to the presence of double bonds. Could you shed light on how this influences their industrial production, Dr. Ayabami?
Certainly, the C=C double bond in alkenes induces reactivity, setting them apart from alkanes. They're primarily produced by cracking long-chain alkanes, which is vital for making polymers and producing hydrogen. This process not only meets industrial demands but also showcases alkenes' role in chemical synthesis.
However, doesn't the unsaturated nature of alkenes also bring about some issues, especially regarding stability?
Good question. While the reactivity makes alkenes versatile, it also makes them less stable compared to alkanes. For instance, they readily undergo addition reactions like ethene reacting with bromine. Despite this, their instability is manageable with the right conditions and is actually leveraged in polymer production.
Looking to the future, how might alkenes play into sustainable technology development?
The promising frontier is in green chemistry, where alkenes are foundational for creating efficient, renewable polymer materials. Innovations such as turning COOH into useful alkenes could drastically cut carbon footprints.
Ethanol serves multiple purposes, from fuel to solvent. Can you discuss its production methods and their environmental impacts, Dr. Ayabami?
Ethanol is produced via fermentation and catalytic hydration. Fermentation uses renewable glucose sources, albeit slowly. In contrast, catalytic hydration of ethene with steam at 300 degrees C is faster but relies on non-renewable crude oil. This dichotomy highlights the trade-offs between efficiency and sustainability.
Is there a robust solution that addresses both efficiency and sustainability in ethanol production?
Challenges remain, but advances in bioengineering could optimize fermentation for speed, reducing reliance on fossil fuels. There's ongoing experimentation with biocatalysts that could potentially alleviate these concerns by speeding up production using renewable resources.
In what direction do you see ethanol's role evolving as we push towards renewable energy solutions?
As renewable energy gains traction, ethanol's role as both a transitional fossil fuel alternative and a substrate for bio-based chemicals will expand, pushing for continuous innovations in its production processes to align with eco-friendly practices.
Polymers are ubiquitous in modern life. Could you delve into the polymerization processes that make them so versatile and what challenges these processes face, Dr. Ayabami?
Polymerization involves linking monomers into large molecules. Two main types are addition, like ethene to polyethene, and condensation polymerization, which produces polymers and small byproducts. These processes create materials critical for everyday applications but raise concerns about non-biodegradability and environmental pollution.
Given these concerns, how viable are current recycling techniques in mitigating pollution issues?
Recycling, though challenging, is crucial. Techniques like breaking down polymers into monomers for repolymerization, as seen with PET, reduce waste. However, the efficiency and public participation in recycling programs remain significant hurdles.
What advancements in polymer science are we likely to see in the near future that could transform recycling?
Innovations in degradable polymers and advanced catalytic recycling methods are exciting fields. These aim to enhance efficiency and decrease reliance on virgin materials, aligning with global sustainability goals.